Welcome back to Lab Cyber. So today's video is going to be more of a quiz, a test to determine your knowledge of AI. So if you think that you know a lot about AI, you think you're a guru, this is going to be the quiz to determine just how knowledgeable you actually are. So what's going to happen here is that the quiz itself is going to be 15 questions divided into 3 different sections. Multiple choice A, B, C, D. So the very first 5 questions would be easy questions just to kind of, get you all warmed up. Ideally, you should score at least 4 out of 5 in this section. And then the next section, questions 6 to 10, this will be more intermediate level, but trust me when I say that these questions are going to be significantly more challenging than the first 5. And then the last 5, that will be the expert level. If you can get all the 5 questions there correctly, then you will have every right to call yourself an AI guru. So the way this is going to work is that I'm going to present to you the question. I'll read out the question to you and the 4 options. And then I'm going to give you about 10 seconds to choose your answer. And then I'll tell you what the answer is and then give you a little bit of some explanation where applicable. So I hope you're ready. Are you ready to test your knowledge? Let's begin. All right, so question number 1, let's get you all warmed up. What does GPT stand for? A, General Processing Technology. B, Generative Pre-trained Transformer. C, Graphical Prediction Tool. Or D, Guided Pattern Training. Your 10 seconds begins now. And the answer is going to be B, obviously, Generative Pre-trained Transformer. It's funny how so many people know about ChatGPT, but they don't actually know what the GPT stands for. Hopefully, you're not one of them. Let's move on to question number 2. Question number 2, what type of AI model is used to generate realistic fake images of people? Decision tree, generative adversarial network, recurrent neural network, or D, Bayesian classifier. Your 10 seconds begins now. And the answer, the obvious answer here is going to be generative adversarial network. Hopefully you got that one correctly. It's not decision tree, it's not recurrent neural network, and it's certainly not your Bayesian classifier. The easy answer here is your GAN, your generative adversarial network. Question number 3, which of these is not a real AI model? Claude, Llama, Mistral, and Neural X. Your timer begins now. And the answer is going to be, well, obviously it's not Claude. Everybody knows Claude. It's not Llama. Most people know about Llama. It's either Mistral or Neural X, and the answer is going to be Neural X because Neural X is not an actual AI model. Don't feel bad if you got this one wrong because I very deliberately chose that Neural X name. It sounds very AI-ish, but Mistral is actually a real AI company. It's French. Neural X, on the other hand, is not an AI model, at least as of the time of me making this particular video. Question number 4, what does NLP stand for? Network Layer Protocol, Neural Learning Process, Natural Language Processing, or Numeric Logic Programming. Your timer begins now. And the answer is going to be Natural Language Processing. Hopefully you got this one correctly. To put it very, very simply, this is what allows AI models to be able to interact with us. It's why we can type in English and Danish, Spanish, whatever language, and then the AI model will understand what it is that we're saying. NLP plays a big role in that. And the last question to round up this very basic section. Question number 5, in AI security, what is an adversarial attack? Is it option A, when 2 AI models compete against each other in training, or B, when subtle input manipulations cause an AI model to make incorrect predictions, or C, a cyber attack that targets AI company servers, or D, when an AI model is retrained with corrupted data. Your timer begins now. And the answer is going to be, well, it's not option A. Okay, you don't have two AI models competing against each other. It's not option C either. It's not a cyber attack against AI company servers. It's either B or D, but the right answer is actually B. When subtle input manipulations cause an AI model to make incorrect predictions. And one thing you should know about the adversarial attack is that AI models are typically most vulnerable during the training phase when they're being trained on data sets. Now, what you have here in the adversarial attack is that you can have a malicious user who comes in and begins to inject this malicious inputs, all just to corrupt the AI model, so it ends up making incorrect predictions or produce biased outputs. That's basically what adversarial attacks are. So that's it, the first 5 questions, the easy questions. Hopefully you got at least 4 of them correctly. Are you ready? Now we're going to jump into the next section, the intermediate section, questions 6 to 10. And like I said, these are going to be a lot more challenging than the first 5 you just faced. So are you ready? Let's get to it. Question number 6. What is the attention mechanism in transformers primarily used for? Is it determining which parts of the input are most relevant when generating output? Or is it allocating more computing power to larger models? Or maybe C, flagging harmful content in AI outputs? Or D, monitoring AI response time and latency? Good luck, your timer begins now. And the answer is going to be A, determining which parts of the input are most relevant when generating output. Now, I do want to say something about the attention mechanism. See, the thing is, it doesn't make models necessarily more efficient at processing outputs. What it really does is that it allows the AI models to understand the relationship and context within the words that make up the user's prompt. That's essentially what the attention mechanism is. So it allows the AI models to focus on the words that actually matter the most, and it allows them to be better at forming context and the relationships between the words, no matter how far apart they are in the user's prompt. So this is a very, very, very useful functionality in transformers. Question number 7. What is the primary purpose of the softmax function in a neural network's output layer? Is it A, converting raw scores into a probability distribution? Is it B, to normalize weights during back propagation? Or C, reduce the number of neurons in the layer? Or D, apply dropout regularization? Good luck, your timer begins now. And the answer here is going to be A, converting raw scores into a probability distribution. Now, the reason why the softmax function is so important is because when you have a neural network that has finished its calculations, maybe for a particular kind of task, it's going to end up with a bunch of raw scores, each one representing a possible answer. Now, the problem here is that these scores can be any kind of number. It could be negative, it could be positive, and sometimes they may not even add up to anything meaningful. So what the softmax essentially does is that it converts them into percentages that will all eventually add up to 100%. So this is why you will have AI models being able to say that, okay, I am 40% confident that this is the right answer, or I am 85.6% confident that this is the right answer. It's all because of the softmax function, a very, very, very useful function indeed. Question number 8. In transformer models, what do keys, queries, and values relate to? Are they database indexing used to retrieve training data? Are they the security layers that will filter out the harmful outputs? or C, the three phases of tokenization, or maybe even D, the three components of the self-attention mechanism? Good luck, your timer begins now. And the answer here is going to be D, the three components of the self-attention mechanism. We just had a question on self-attention mechanism a bit earlier. Remember, it's what allows the AI models to establish context and the relationship in the words. So what typically happens here is that in your prompt, each word would have a query, a key, and a value. So essentially, the query would say, okay, what should I pay attention to? The key will say, okay, here is exactly what I am. And then your values will actually deliver the actual information once a match has been found. That's how all these three come together to provide context and relationship for the words in your user's prompt. So D is the answer, the three components of the self-attention mechanism. Question number 9, what is temperature in the context of LLM inference? Is it the heat generated by GPU clusters during training? Is it B, a measure of how much training data was used? Is it C, a parameter that controls randomness in token selection during output generation? Or D, the latency threshold before a model times out? Good luck, your timer begins now. And the answer here is going to be C, a parameter that controls randomness in token selection during output generation. Now, the thing about temperature here is that it's a way of determining how creative you want a model to be. So when you have very low temperature, your AI model will end up going with the safest answers, the safest outputs. Creativity is going to be a bare minimum. But when the temperature is very high, now you can have the AI model begin to take more risks. They become far more creative. Unfortunately, though, the more creative they are, the more likely they are to begin to hallucinate and then make mistakes. So you always want to make sure that the temperature is dialed in correctly, depending on what the user's prompts are. If the user is asking for the answer to like a factual kind of question, obviously you want the temperature to be very, very low. But if the user wants the AI model to become very, very creative, then obviously you want the temperature to go higher. So again, the answer to this is going to be C, the parameter that controls randomness in token selection during output generation. And question number 10 to round up this intermediate section, what problem does the vanishing gradient cause during neural network training? Is it A, the model generates repetitive outputs? Is it B, early layers stop learning because gradients shrink to near zero as they propagate back? Or is it C, the model overfits to training data too quickly? Or maybe even D, the GPU memory runs out during large batch training? Good luck, your timer begins now. And the answer here is going to be B. Early layers stop learning because gradients shrink to near zero as they propagate back. Now, what happens here is that in training or in learning, when a neural network makes a mistake or an error, it tries to learn through a process known as backwards propagation, where error signals will be sent backwards. Okay, so the latest neurons will get the strongest signal, but then as that signal begins to go backwards through each neuron, the strength of that signal starts getting less and less and less until eventually it disappears. It's finished before it reaches the earliest neuron. So that's basically what the vanishing gradient problem is. All right, so now we're going to jump into the last 5 questions of this quiz. And like I said in the intro, if you can get all 5 of these correctly, congratulations, you are a certified guru in AI. Let's begin. Okay, so question number 11. What is catastrophic forgetting in neural networks? Is it A, when a model trained on a new task loses performance on previously learned tasks? Is it B, when a model deletes corrupted training data automatically? Or C, when gradient explosion causes a model to reset its weights. Or D, when a transformer model runs out of context window during inference. Good luck, your timer begins now. And the answer here is going to be A, when a model trained on a new task loses performance on previously learned tasks. Now, the natural question here would be, why does this even actually happen? Well, that's because neural networks, when they're learning, they will store their knowledge in their weights. Now, when you try to retrain them on a new kind of task, those weights might end up being overwritten, and there is no sort of mechanism to ensure that the old knowledge is actually stored and kept safe in some other location. So that's exactly why sometimes you do have this issue of catastrophic forgetting. Question number 12. What does perplexity measure in a language model? Is it A, the ratio of correct to incorrect predictions on a test set? Is it B, how many parameters a model uses per token generated? Is it C, how uncertain a model is when predicting the next token? Or D, the computational cost of each attention head? Good luck, your timer begins now. And the answer is going to be C, how uncertain a model is when predicting the next token. So perplexity essentially just measures how surprised a model is by the next token. So a well-trained AI model on familiar text should really ever be surprised. So essentially, the lower the perplexity, the better trained or the more confident the AI model is going to be. Question number 13. In federated learning, what is the primary privacy advantage? Is it A, all data is encrypted using homomorphic encryption before training? Is it B, users can opt out of contributing data at any time? Is it C, training is performed exclusively on synthetic datasets? Or is it D, the central server never sees raw user data because only model updates are shared? Good luck, your timer begins now. And the answer here is going to be D. The central server never sees raw user data because only model updates are shared. So normally when you're training an AI model, what happens here is that all your data will get sent to the central server. But let's assume, for example, here that your mobile device here is being used to train the AI model. What happens here is that the AI essentially will come to your device, train locally on your mobile device, and then only send back what it has actually learned. The raw data from your device itself is never sent back to the central server. So the server just ends up collecting all the lessons it has learned from millions of other, similar devices or smartphones and ends up improving the model. Your own raw data or the raw data of all those other devices never actually leaves the devices themselves. And that's why it has this primary advantage when it comes to privacy. Question number 14, the penultimate question. What is a model inversion attack in AI security? Is it A, querying a model repeatedly to reconstruct sensitive training data from its outputs? Is it B, feeding adversarial inputs to flip a model's classification output? Is it C, reversing a model's weights to steal its architecture? Or D, injecting malicious prompts to override system instructions? Good luck. Your timer begins now. And the answer here is going to be A, querying a model repeatedly to reconstruct sensitive training data from its outputs. Now, this is one of the more common attacks. It has actually occurred several times already. Now, what happens here is that the malicious attackers, they can't see the actual raw data with which the AI model was trained on. However, with the model inversion attack technique, what happens here is that they're going to end up querying the AI model thousands, maybe even tens of thousands of times, and then analyzing its responses. Okay, so by analyzing the kinds of outputs the model gives back, the malicious users, they might be able to reconstruct sensitive information from its training data. That's essentially what the model inversion attack is. And the final question, good luck. This is question number 15. What is the lottery ticket hypothesis in deep learning? Is it A, random weight initialization always produces unpredictable model performance? Or is it B, within a large neural network exists a small sparse subnetwork that if trained in isolation from the start can match the full network's performance? Or is it C, larger models will always outperform smaller ones given the same dataset? Or D, dropout randomly selects winning neurons to improve generalization? Good luck, your timer begins now. And the answer here is going to be B, okay? And I know this might have been a bit obvious given the fact that it's the longest answer, but it is in fact B. So what this lottery ticket hypothesis is that typically when you train a massive, large neural network, most of it turns out to be redundant, all right? So this lottery ticket hypothesis says that hidden inside this your massive neural network, you're going to have a much smaller subnetwork that actually does most of the heavy lifting. So it's kind of like a lottery. You know, most lottery tickets, they lose, okay? But then you'll have a few winning tickets that does most of all the work essentially, right? So if you could identify and then just train that small subnetwork from scratch, that same subnetwork that does most of the heavy lifting, you're going to get the same performance at a fraction of the size and cost of training, you know, the large neural network itself. So that's essentially what the lottery ticket hypothesis is. All right, so that's it for the quiz. How many did you get correctly? Put your answers down in the comment section below. Don't lie, be honest, okay? It's perfectly fine if you only got one or two of these questions correctly, especially in the latter sections, the sections 2 and 3. Those questions were quite challenging. You really do need to know your AI stuff to get most of those questions correctly. And if you got all 5 questions in the final section correctly, I'd love to hear from you. Go down in the comment section and brag about how you are indeed an AI guru. So that's it for today's video. Please share the video, share this quiz with anyone you feel might be interested in it. If this is your first time here on the channel, welcome to Lab 7. My name is Alex. I cover topics, tutorials, news in the world of AI and cybersecurity. So if you do enjoy content like this, be sure to subscribe to the channel and hit the bell so that you're notified whenever I upload a new video or a new quiz. Stay safe out there, and I'll see you next time. Cheers.